All right, welcome. Thank you for coming here. So I wrote a functional Perl together with Samuel. So I'm a PhD student at Chalmers. Samuel is a master student. Helped me out a lot. Right, so I'll present a hack today. It's the kind of thing that I was surprised that it worked at all. Okay. I don't know if I'm picked up. It doesn't matter, right? I'll just hold it. Okay. All right. Great. Right. Yeah, it's the kind of thing that where I was surprised that it worked at all. So this is a Perl, and I've never written a Perl before. I've written papers, so I was trying to figure out, what should go in a Perl that doesn't go in a paper, or the other way around. And I found some common keywords. So a Perl is supposed to be fun. It's supposed to be educational, right? You should learn something. And another keyword that comes up is that it's supposed to be elegant. And this is kind of something that, I haven't focused too much on this in this presentation. So don't expect too much elegance, but rather just, try to see the fun in this. So kind of case study that I'll use throughout this talk is, so I'm going to talk about HasChor. This was presented last year at ICFP. It's a Perl. So HasChor is a framework for writing choreographic programs. So that is so you write a single kind of compilation unit where you describe the actions of multiple endpoints in a distributed setting. So you write code for many different endpoints. And HasChor, so I haven't changed the API of HasChor at all, just the implementation. So if you remember the details from last year, they shouldn't have changed, but I'll just go through them quickly anyway. So the primitives of HasChor, there are quite few. So you can have values that are tagged with a location, like which endpoint this value exists at. And then you have 3 API functions. So you can say that a function, an endpoint locally performs a specific computation. So the other actors in this distributed application, they're not going to run this local computation. You can send values from one endpoint to another. So it looks like a regular arrow, but it's actually like a little squiggly arrow. And then you can have this sort of synchronized branching. So if a located value, if you branch on that value, you want to inform all the other endpoints of which branch you picked so that you can synchronize sort of further communication. So showing this API through an example, so you identify endpoints through proxy types essentially. So you have these type level strings where you use the strings to identify endpoints. So it's quite straightforward. And here's the type of locally, so you don't have to think too much about the middle line yet. But so the first argument is one of these proxy types, which identifies which endpoint is supposed to run this local computation. And the second argument, you see that it ends with MA, so that's kind of like the monadic computation that we're supposed to run on this endpoint. And the result of the whole thing is in the choreo monad, choreographic monad, and the value is a located result, right? So it's A at L. So L performed this local computation, so of course the result resides at L. So here the client, for example, is locally, so the client locally is going to prompt the user for a password, and then just read a line from the terminal. And the result of this whole thing, the type is choreo IO of string at client. So the result here is a string on the client endpoint. So the other endpoints cannot observe this value. The second function, the communication, so it takes a tuple of an endpoint and a value at that endpoint, and then it just takes another endpoint, which is supposed to receive this value. So for example, if the client wants to send this value to the server, you just put this little squiggly arrow there, and that'll happen. So the type of S is now string at server. So we kind of communicated this string from the client to the server. And the last function is this sort of conditional, synchronized branching on a value. So you can think of this as casing as a value. So again, you take a tuple of a location and a value at that location, and then the function which handles that. So for example, the server might want to locally check if the password is Haskell Symposium. And now we see here this parameter. Maybe I can use the arrow. Can you see this? Yes. So this parameter to the local function is an unwrap function that we can use to unwrap located values. So this is supplied by the implementation, and this makes sure that you don't unwrap values that are not located sort of on your endpoint. Right. And then you can use this cond operator to case on true and false. I'm sorry for the lambda case, Leonard. but the choice that is made here, which branch to take, that's sort of propagated to all the endpoints, because you might have further communication in these branches, and you kind of want to sync up those calls. So this is the HasChor API. So I haven't changed this at all. So how is this implemented? So HasChor is implemented using freer monads. So I'm not gonna, you don't have to know the details of the freer monad, but I'll tell you that you need to define kind of like a signature identifying what effects the like this monad is supposed to perform. So we have 3 effects here, right? We have local computations, we have communication, and we have this synchronized branching. And the types here correspond to the ones that we saw on the API functions as well. And then the choreo monad is just sort of the freer monad over the signature. It's quite straightforward. However, we noticed that, so if we have a value of this type, this choreo sig, we have a value that describes the actions of all the endpoints in our choreography. But when we actually run this program, we'd like to say, so now we want to run this endpoint, right? We want to run the client. But the client doesn't do all the operations, right? So we're going to have to project the client endpoint out of this whole thing. And we're going to build a value of this more primitive type network. So this has more, common network operations, sending, receiving, and broadcasting, and then run for lifting monadic computations. So if we consider just, for example, the communication operation, so this involves 2 endpoints, right? A sender and a receiver. So there's communication between 2 endpoints. So for one of them, this is going to be a sending operation, and for the other one, this is going to be a receiving operation. So what HasChor does, so this is kind of like a diagram of what happens right now. So the dotted line here represents what happens during compilation. So we write our choreography, and when we compile it, we get this executable that kind of contains code for all the different endpoints, right? Because we don't know yet which endpoint we're going to project. Then at runtime, we're going to kind of use EPP endpoint projection to say, well, okay, we want to run the 4th endpoint, for example. Now, so what does this EPP function look like? So we're kind of almost done with the prelude here. So it's quite a simple function. So it takes the choreography, right? And this located term here, you can think this is a string, okay? So this L prime here, that's the endpoint that we want to project. So for example, in the cases here for communication, we have a sender and a receiver. And we have 3 cases. So if L prime, if we are the sender, well then we perform the sending operation. And this is in the network monad. If we are the receiver, we perform the receiving operation. But it might also be the case that we are the 3rd wheel watching 2 other endpoints communicate. And in that case, we are not supposed to do anything, right? So this is a no-op for us. Now, so when I saw this last year, I thought, wow, it's a shame that all of this happens at runtime. Because we had this situation here where the binary has code for all endpoints. And I thought that's a bit wasteful, right? What if one endpoint has really messy dependencies, or what if one endpoint is really expensive in terms of the size of code it uses or whatever. So as a diagram, what I'd like to do is extend this box to just sort of, so we run endpoint projection during compilation, hopefully shaving off all the other endpoints that we don't need. So why would we like to do this? So last year I wrote a paper with my colleague Abrup, and we wrote Haskell code describing the actions of a client and a server, and we ran the server component in a hardware-enforced trusted execution environment. And here it's kind of a security constraint that we want to put as little code as possible in this enclave. We don't want to have any bug where we're tricked to jump to code that is malicious, right? Or buggy. So if the code is not there, we can't be tricked into jumping to it. So that's kind of why I want to do this. So I asked myself, right, this is a diagram of what I just said. So I asked myself, right, and this is what we want to do, sorry. Last year we had this very simple setup with a client and server, but choreographic programming, it's more general, so the endpoints are not necessarily clients or servers, they are all on sort of an equal standing with each other, and they have the same capabilities. So we'd like to compile this application several times and get one endpoint in each binary. And I ask myself, is there, by any means necessary, can we do this, right? Can we partition this program? So the first thing that I observed is that this choreo signature is quite problematic, right? Because this builds up the structure containing all the actions, and then after that we project one of them, right? So what if we just sort of chuck this away and just say that the choreo monad is now the network monad, right? So we never, let's say that we just never build this intermediate structure. And endpoint projection, so if we now kind of consider this pseudocode here, so I'll modify this a bit. So what if we say, so this is the function we want to run at compile time, right? We'd like to run this function at compile time. So what if we say, well, let's just fix L prime to be client, right? So, you know, if we want to project at compile time, we also have to fix the endpoint we want to project. The clauses, the cases, you know, somewhat becomes like this, right? So we kind of know here that, okay, if the sender is client, we know that we want to do the sending operation. If we are the receiver, we know we want to do the receiving operation. So in order to run this at compile time, we will turn these equations into rewrite rules. This is kind of where, you know, it becomes a hack. So, okay, we'll write our rules, right? So for any term client of this type, proxy client, and it's very important here that we have this type information here. So if client is part of, you know, if client is sending here, well then, you know, just rewrite this to do the sending operation. Similarly, if you are the receiver, we have this third case here, right? You know, if we're not part of the operation at all, just do nothing. So, okay, what if we just add like a rule here, you know, okay, well, for any other sender and receiver, do nothing. So does anyone see any problem with this rule? I see some people nodding, so I'll just say that the problem is that if any of these rules matches, this rule for sure also matches. And GHC, the documentation says that if more than one rule matches, I mean, that's fine, but GHC is free to pick whichever rule it wants. So this rule is, of course, we might pick this one when we'd like to pick one of these. All right, what if we enumerate the two cases here? Let's say that we have a third node, a third endpoint called node, right? What if we, okay, well, we have a case for when it's a sender and one case for when it's a receiver. Is this better? Does this work now? So this is also problematic because, for example, here the client is the sender, right? So we know what to do. But it might be the case that client is sending to node, and then, yeah, this rule also matches, right? So this is problematic. So if we have these three endpoints, to sort of exhaustively have our cases here, we'll have to create a quadratic number of rewrite rules. So I've left out the cases here where client sends to client, for example, but we have those cases as well. And okay, of course, you might think, you know, you can't write that many rules, right? And you're absolutely correct. I'm sorry, Leonard, but we're using template Haskell. So we can, yeah, so I don't know, this is amazing. I didn't know this, but you can generate rewrite rules at compile time that will then be used throughout compilation. And you can just generate however many you want. At some point, I guess GHC will just crash, but yeah, this is amazing. Okay, so okay, I write some template Haskell, right? So you just write this now, this function compile for, and you have a list here identifying your endpoints and where to find them in the network. And you have this number here just saying which of these three we should project. And that's going to generate, okay, so 0 means we project the client endpoint, and then we're going to generate rules that projects the client endpoint. Okay, and this is great. So this works wonderfully. So this is our original, the code, the HasChor example we had. And after sort of running our rewrite rules, this is what we'll get. So for example, the red thing here is the server local computation, and that just became a sort of empty computation here. So the code that was in here, and every, you know, if we had like a unique dependency to this code block, that's just gone from the source code now, which is great. So we're kind of, you know, operating on the compilation source, right? So we're not running the function, but we're sort of, you know, applying them one rule at a time. Yeah, right. And the sending, yeah, the communication call here became a sending operation because we know that we are the client and we'd like to do a send here. Okay. So I have I wrote a core plugin as well, just to, you know, what, you know, do we, after compilation, do we, like, are we sure that we really partition the program? So if we successfully partition the program, there shouldn't be any calls to these API functions in the code anymore. Like if we have such a call left, yeah, at least one rule didn't fire. So I wrote a core plugin, so it installs itself last after all optimizations, just before code generation. And it just looks for calls to these functions. And if it sees one of these functions applied to any parameters. It's just gonna throw an error. Yeah, partitioning didn't work, so try again. So that gives us, I don't know, some sense of confidence of whether this worked or not. We can also just run the code and see if it works. But yeah, this is a bit more, I don't know, I'm not going to say stable, but yeah. So HasChor has a very nice feature that you can write location polymorphic functions. This is a tiny little function. So it has the proxy, it takes a location as an argument. And the type of this L here is, it's like known symbol L. Like we just know it's an endpoint, but we don't know what the endpoint is, right? So this function locally, that endpoint is going to read this mvar and just print the contents, and then recursively call itself. And we have, this is some, I'm just listing our rules here in a shorthand format. So we have, rules for locally, right? We know what to do if we have the client server node. But if we look at P here, the type of this is known symbol L to proxy L. So there's no rule that matches this, right? So we can't, so this function we can't actually partition. So that's a bit problematic. But we can specialize the function to a particular type. So, of course, we'd like to specialize the function to all the possible types. But yeah, so here this is again, and we just write this specialization pragma. For example, for the client, let's say, okay, we'll specialize this type to client. So we'd like to generate these things as well with template Haskell. What this will do is it will emit a specialized version of loop print with that specialized type. And now the type of P in this version is proxy client. So now we know which of these rules that we should apply. It will also emit a rewrite rule. This is how specialization works. So we'll emit a rewrite rule as well. So when we see a call to loop print with the term that matches this type, proxy client, we'll just rewrite that to call this specialized version instead. And this function, after specialization, the first step, it's no longer recursive, right? Because it calls loop print instead of itself. But this rule is going to fire and make sure that now, after further optimization, it's now recursive again. So we use specialization here to reintroduce the missing type information so that we can partition the specialized version of the code. And if you saw Simon's talk yesterday, like the new specialization syntax, you can just write, at the term level, expression level, apply this top level string instead, type level string instead. So an example in the paper of where this made building easier, so I'll just sort of go through this. So there's the box contains the code that is actually a HasChor program. So we have a server written in C running somewhere else. This is not part of the choreography, but it's part of the application. So this authenticator endpoint is going to establish a Bluetooth connection to this server. And when that happens, the server will send some code, like a SMS, a text message to you or something, with a code. And the client sort of enters that code, sends this to the authenticator, which sends it back to the server. This is kind of the protocol. Now the server will verify that the user who got the code actually sort of, is the client here, and then you can get an access token back. So the authenticator is doing this via Bluetooth. So I'm using the Blues sort of Linux stack to access the Bluetooth chip on my computer. So you don't have to read all of this code. This is the whole code for the choreography here. So the blue parts are Bluetooth code. And I just want to show here that only the authenticator endpoint is actually using Bluetooth. So after projecting the authenticator application, applying our rules, we use the Bluetooth, we get those through like foreign functions. So this is the version of the code after we projected the authenticator endpoint. And we see that the Bluetooth code here remains, right? Because the authenticator had to call the Bluetooth code. But the client, after projecting that, there's no longer any references to Bluetooth, the Bluetooth foreign function calls in here. So when we compile this and partition, so GHC will ask us for this source when we are compiling authenticator. But if we don't export those foreign function calls, the client will be perfectly happy to compile without that the Bluetooth source. So if this is an example of, let's say that this is a super tricky dependency that maybe the machine the client runs on doesn't have this dependency, or it's just very messy to build it. So in this case, sort of, we don't need that dependency anymore on the client, and that's recognized, and we don't, so building became easier. And a reviewer here asked a very good comment, like, do you still need to mention this blues library in the Cabal file? That's a very good question. So yes, you do. So what I did here, so when I wrote this, I just wanted to see, if I can do this without actually mentioning this in the Cabal file. So I just used this, sort of, I dynamically opened the shared object at runtime. If I find it, great. Otherwise, it just crashes. But yeah, now you don't need to mention it in the Cabal file, but it's, substantially more shaky, of course. Right, so some sort of notes on this. So it's absolutely a hack, right? So, I never expected this to kind of work, but I could compile all the examples from the HasChor that went with the HasChor paper last year, and this additional one that I wrote, and some other sort of toy examples that we wrote along the way. So we have to be a bit careful with what we export, right? Because we want to sort of eliminate code, right? And if we somehow end up exporting the function that we wished to partition, that will still end up in the object file, and it will end up in the binary. And if that object file requires extra C sources, it will ask for them. But we can get away from some of this by using this split sections flag, which puts every function in its own section in the object file, and dead sections unreferenced sections are dropped at linking. So I say in many cases here. So the documentation says this flag works on sort of platforms where this the object format supports sections. But the documentation doesn't say which platforms this is. It works on my laptop, but yeah, I don't know much more than that. And there, of course, you can contrive a program where this approach doesn't work. So the one example that we couldn't run from the HasChor program was like a ringleader protocol, where they use this type. So they define a type edge that sort of internally on the inside has these two proxy types, and we can't write a rule for edge that kind of matches on these on the inside. So yeah, we couldn't partition this program without rewriting it. So the general takeaway of this is that the API kind of defines the borders, right, of partitions in your program, and then the rewrite rule, that's what we use to actually do the slicing and partition this program. So yeah, I hope you like this hack.
Hi, great talk. So I was wondering, in the spirit was making this less of a hack, if I'm going to use this, it's very important for choreographic programming that when someone is sending, the one is receiving, right? Do you see a way to connect the original way HasChor was designed, where all the endpoints were embedded in the binary, with your stuff, like a quick check property or something like, to make sure that what I'm doing, I'm getting the same thing?
I don't know. So my first thought is that I haven't really changed what they're doing, right? I'm just running it at a different, like this endpoint projection, right? We assumed that it worked for HasChor, right? And I haven't really changed this function.
But you did some tricks to get right the rules, right?
Right, yeah.
To get the rules. Maybe in
you
the
mean
future,
the specialisation?
Yeah.
Yeah, but
exactly.
for that, so we have the plugin to say no if partitioning didn't happen. So I guess we just won't run that program if it didn't happen. But there's no, I haven't really thought of how we can, gain more confidence in
that. You didn't skip any send or any receive, or you changed.
No. So I can't remember now, but I think so. Someone showed me even a HasChor program. Like you can write a HasChor program, of course, that sort of doesn't work. I'm sure you can still do that here, of course.
Right.
Yeah.
Right.
Hello, Jaro again from TU Delft. Have you considered using your plugin to actually apply the rewrite rule and in that way get the right ordering?
Sorry, what do you mean?
There was a problem with you having to generate a quadratic number of instances of rewrite rules to do this projection.
Right.
I thought maybe you could use the GHC plugin mechanism to manually specify this ordering of.
Right. So I think I discussed with my advisor, and I think we came up with like a way of generating a linear number of rules. We just haven't had time to implement it.
Okay.
And it's only this rule with sender that has this, of course, because there's two endpoints here. The other two are perfectly linear. But yeah.
Yeah, I was also thinking in the context of stabilizing the GHC API. I think I've also wanted sometimes to be able to manually apply rewrite rules in GHC plugins. But
I don't know, it feels like I would duplicate what the rewrite ending already does, or?
Well, then you can't specify the ordering of the rules, and you can also not, you could add extra conditions to when you actually want a rewrite rule to fire. But if you don't need it, then I guess it's not necessary.
It's a mess, yeah. Yeah.
Hi, I'm Grant Van Donlen, Portland State University. So in your Bluetooth example, you kind of had 3 machines involved in this like computation system, but only 2 of them were in the choreography.
Yes.
I think you could kind of imagine a choreography with all 3 of them, but I think HasChor limits you to having one backend that they all communicate
Yes,
through.
yes, you have to pick one backend that everyone uses to communicate, yes.
Yeah, but now that you're kind of you're generating a separate implementation for each pair of endpoints, could you imagine having like multiple backends so that these could all be part of one choreography, but you specialize the send and receive to a different backend depending on which endpoint that you're using?
I think not now, but because you know each, even though yes, I mean you're compiling, you're saying I want to specialize this endpoint, right? And then you say I want to use this backend, but then that endpoint is going to use that backend to try and talk to everyone, right? So I don't. So right now the API doesn't let you say with this endpoint use this backend, with that that backend. Maybe you can do that, but right now no. I think it would be you know more work than just sort of letting you say that. Yeah.
Okay, thank you.
Hi.
Hey.
I have a question which is I think very similar to what Yara was asking. If I remember correctly, it's been a while since I last looked at them. There is a way to like attach sort of numbers to rewrite rules to say in which phase they should run.
Yes.
Would that also work to like attach like the last phase to your catch or none of the other rules fired, so just do empty?
Oh, I don't know. Maybe, yeah. I think I would have to sit down and try it out, but maybe yes. I'm not sure. I'm not quite sure, but I'm not. I'm not, you know, sure of a no. Yeah.
All right. Well, so I guess I just have to ask. You know, I thought for a bit you weren't going to have any template Haskell at all, and I was like, oh, that's cool. This makes Leonard happy. But then the template Haskell arrived anyway. So then that sort of seems to beg the question: could you do the sort of partitioning purely in template Haskell, right? And then you'd be able to sort of generate multiple partitions in the same program. You'd have exact control over sort of how you manipulated the program, you know, whether you transform the type while you transform the program and so forth. So did you evaluate that approach?
Yeah, I mean, yes and no. It's not in the Perl, but in the Perl we have another case study as well. It's a slightly simpler API where we have separate modules giving each implementation. And I have code where I generate these complete modules with template Haskell instead, and each module has this specific. But for that, so that's not in that extension is kind of not in the Perl. But for that trick, we're kind of relying more on dead code elimination and stuff to actually partition. Whereas here it's a bit more explicit, but yeah, it's a hack, right? And kind of you're just using kind of GHC's toolbox to make it happen. So I don't know. Yes and no. Yeah.